Right, so we're going to finish up section 6.4. Okay, we left off, we talked about the formula to find the period, because tangent and cotangent naturally cycle a little bit faster. They cycle at pi units. The formula to find the period is pi over b. And again, if you need a reminder, b is always the number in front of x. And c is really a vertical stretch. Again, we don't talk about amplitude as much with tangent and cotangent because they go up and down forever. So there is no way to measure the height. Okay, so it's just a vertical stretch. All right, so there's a chart that we're going to use to figure out how the asymptotes are going to move. Because when you do a transformation, everything moves. Right? The graph moves, the asymptotes move, the intercepts move, everything moves the same way. So how would we figure out where the asymptotes are going to be if we do a transformation? Well, the first step is to know where the original asymptotes are. Okay, I'm going to show you guys this chart again in a little bit, but I just want to focus on the tangent and the cotangent part. In order to describe where the new asymptotes are going to be, because remember, there's infinitely many of them. We can't list them all out. We need to describe them with a formula. As long as you know where one of the original asymptotes is, you can describe where all the asymptotes are. So let's look at, for example, tangent. Tangent has an asymptote at pi over 2. So let's go back to our graph of tangent. Let's take a look at it. And I might have to just sketch it real quick. So there's an asymptote at pi over 2. Here's another one at 3 pi over 2. Here's another one at 5 pi over 2. What's the distance between asymptotes? John?
Would be pi units.
Pi, right? It's pi radians. That's the distance between asymptotes. So if you tell me that there's an asymptote at pi over 2, and I wanted the next one after that, what would I add to that number to get the next one? Yep? Pi. What would I add again to get the next one? Pi. And what would I add again to get the next one? Pi. So the point is, you can add pi n times, and that will give you an asymptote. You can add it one time. You can add pi times 2. You can add pi times 3, pi times 4, and it'll keep giving you more asymptotes. You can also do pi times -1. That would give you that asymptote. If you added pi times -2, which is really subtracting 2 pi, that would give you that asymptote. So the point here is you can describe all the asymptotes of tangent by this formula, adding or subtracting an integer multiple of pi. You can't add 1.3 pi. That would land you in the middle of an asymptote. You can either add a full value of pi, or you could subtract the full value of pi. And you'll always be at another asymptote. That's for the original tangent. What we want to look at now is when you do a transformation. How do you describe it? Okay. Question? So when we do a transformation, let's go back to this table. The first thing you have to do to find the new asymptotes is figure out where one of the asymptotes is. It doesn't matter which one. As long as you find one and then tell me, okay, here's one, you can move forever left and right from that one and you'll hit them all. Okay. As long as you have one. Well, how do we find one of the new asymptotes? And this is what I think we started in this class yesterday, and we'll take a look at this again. How to find asymptotes when you do a transformation. The first step is start with the original asymptote. How are you going to know that? You've got that table from the other page. That will tell you the original asymptote to start with, depending on which function you're working with. We've only done tangent and cotangent so far. Next, you want to figure out where does that single asymptote move under the transformation you're doing. That's what step 2 does. Set the original asymptote equal to the argument and solve. Now, after step 2, you know where one asymptote is in the new function. You know a single asymptote. Now, from that one, you have to describe all the other ones. How often does an asymptote occur? Every cycle. Every cycle, you're going to get exactly the same behavior again. So to describe all the asymptotes, we take the one that we found from step 2, and we put plus the period times n. You can write period times n or n times period. It doesn't really matter. N just stands for an integer multiple of the period. And that's what I had you guys describe with the original tangent function. Pi over 2 plus pi times n. Or I usually like to write it n times pi. Same thing. So let's try an example. We might have done this one yesterday, but let's try it again. And this time, I just want to describe the asymptotes. Okay. We'll do that, and then if we want to graph it, we can go through the graph again. And I'll pause at that point, make sure those are unlocked if you need them. All right. What is an asymptote in the original tangent function? I don't care which one you give me. I just need one asymptote in the original, any asymptote. Preferably, I like the smallest one, but yeah.
Pi over 2.
Pi over 2. That's the first positive asymptote that you come across. Let's figure out what happens to that asymptote under that transformation. Just want to see what happens to that one. That's it. So, we take the asymptote, set it equal to the argument, and solve. What's my argument in this one? John?
2x.
What is it?
2x.
2x. Now, think about what putting a 2 in front of x should do. That's a horizontal... What's the 2 going to do? Michael?
Compression.
That's a compression. So the asymptote, if it was a certain distance away from a point, let's say the asymptote was right here, and you're compressing, well, that's compressing by a factor of 2. So now the asymptote should only be half the distance that it was before. Right? Everything is going to get squished. If you think of 0 as kind of the point that doesn't move, everything is going to get squished towards 0. Everything's going to become half the distance that it was. So let's solve and see if our asymptote follows that logic that I just said. So to solve this, Tim, how would we solve this?
Well, you divide each side by 2, which would make it pi 2 times 1/2, which basically would mean pi over 4.
Yeah, so when you divide each side by 2, it's like multiplying by a half, and we get a new asymptote at pi over 4. Follows exactly the logic we just said. It used to be at pi over 2, which is 90. Now it got squished down to 45. Okay. But that only describes one asymptote. How often is the asymptote going to repeat just in general? Or how often does anything repeat in a trig function? Every period. Okay? Every single period you're going to get another asymptote. So we would have pi over 4 plus any multiple of the period. You need to find what the period is and put that in. Tangent 2x. What's the formula for calculating the period of a tangent function? Yeah, Maddie?
Pi over b.
It's pi over b, and in this case, pi over 2. So the way you would describe all the new asymptotes in this graph is you're going to have one at pi over 4. That's the first positive one you'll have. And then that asymptote will repeat every pi over 2 radians.
So we need to write equal to x.
Yeah, if you wanted to write it as an equation, that would be the proper way to do it, yes. Because vertical asymptotes always start out with x equals. Yep. If you think of it in degrees, what this is saying is your first asymptote is at 45 degrees, and then every other one is 90 degrees away from it, left and right. Okay, so any question on that equation? And then if we wanted to find a graph that shows 3 cycles, well, what did we just say that the period was? Michael?
Pi over 2.
And if you triple that, what do you get?
3 pi over 2.
3 pi over 2. So the easiest way to show 3 cycles would be to set your window to triple the period. Now you'll see 3 cycles. Remember, range isn't as important on tangent because it's going to go up and down forever. So let's just type it in. Tangent 2x. I think my range is -4 to 4, which is fine. That's a half cycle, full cycle, half cycle. So technically that is 3 cycles. It's just they're not all connected nicely. But that's okay. Any questions on that? All right. Okay, so here we've got 2 graphs. Okay, this kind of thing is definitely important for the test. And all I want you to do is identify which one of these is the graph of 2 tangent x and which one would be the graph of 5 tangent x. As long as you know what the transformation is doing, you should be able to identify which one is which. Anyone have a thought, Nick?
Left is 5 tangent x
Okay, how come?
because it's a vertical stretch and that one's steeper.
Yeah, that 2 and the 5, they're both doing a vertical stretch to tangent. So imagine you had something that was curved, like a piece of wire, and you pulled on the top and the bottom. It would start to look like it's straightening out a little bit. It never really would be completely straight with tangent, but it starts to look more like it's straighter and less of a sharp curve. So on the left is the 5 tangent x. On the right is the 2 tangent x. Any question on that one? All right. So now let's take a look at secant and cosecant. How can you type in cosecant on the calculator? Because there is no CSC button. John?
Would it be 1 over secant?
1 over secant? We don't have a secant button on the calculator.
Oh. Oh, no, sorry, it would be 1 over sine.
1 over sine.
Yeah.
That would give you cosecant. And how would you type in secant? Michael?
1 over cosine.
1 over cosine. Now, do the graphs of sine and cosine have any x-intercepts?
Yeah.
Yes, so what does that mean? What's going to happen here if the graphs of sine and cosine have x-intercepts? We're going to have asymptotes, because where you have an intercept, that's where the y value of the function is 0. You can't have a value of 0 in these fractions, because if you did, it would be undefined. So when we graph secant and cosecant, we're going to have asymptotes. At sine, remember the roots are 0, pi, 2 pi, 3 pi, 4 pi, every multiple of pi. So let's look at cosecant, and you're going to see an asymptote at every multiple of pi. So here is cosecant. It's harder to see on the graph, but I did label them down below. There are asymptotes at 0, pi, 2 pi, 3 pi, and so on. And then for secant, you're thinking about where the graph of cosine would cross the x-axis. That's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. It's all odd multiples of pi over 2. I guess if you wanted to kind of say it in a uniform way, you could say that secant is the odd multiples of pi over 2, and cosecant is the even multiples of pi over 2. Now the question here is, how many asymptotes per cycle? You gotta think of that idea like, you can't have something belonging to 2 cycles, but every cycle has to have the same amount. Nick?
1.
Okay, so here's a full cycle, okay, inside this box. A cycle of secant and cosecant consists of 1 full U shape and 1 full N shape. That's a full cycle. So if we said that that cycle only has 1 asymptote, then maybe I would say, okay, that one belongs to it. But the problem we would have is the one in the middle then wouldn't belong to anything. So anyone have another thought about how many? Yep.
3 asymptotes.
Okay. So let's take this box and move it right there. So let's say all 3 of these asymptotes, 1, 2, and 3, they all belong to that in the red box.
I get why, because then they won't count for the next ones.
Let's put another red box.
So it's only 2.
Well, that box has to have 3 asymptotes too then. If we're saying 3 asymptotes belong to the box on the left, then the box on the right has to have 3. Well, I agree it could have these 2, but I don't agree that this one could belong to it because it already belonged to something else. So, any other thought about how many asymptotes per cycle? Yep.
2.
It is 2. And it doesn't matter how you think of it, like which 2, but generally the one in the middle, I mean, that's pretty clear cut. The one in the middle belongs to that red box. And then think of it as either the one on the left or the one on the right, but not both. Okay, but the point there is there are 2 asymptotes per cycle. The first 2 positive ones for secant are pi over 2 and 3 pi over 2. And the first 2 positive ones for cosecant are 0 and pi. Now, let's look at, it doesn't matter which one we look at, but we know this is 0, this is pi, this is 2 pi. Those are 3 asymptotes I just labeled. Here's a cycle. What is the distance from the left edge of that box to the right edge? Nick?
2 pi.
2 pi. So secant and cosecant have the same period as sine and cosine. So to find the period of the secant and the cosecant, it's 2 pi. Technically, it's over the absolute value of b, because when you're finding the period length, it is a length. You should not give me a negative number, ever, for the length of the period. But I told you yesterday, or maybe the day before, we weren't really studying examples with sine and cosine where b was a negative number, so you never really had to worry about it. But if b is a negative number with the secant or cosecant, take the absolute value of it when you're finding the period. So tangent and cotangent are actually the 2 that are kind of weird. They use pi over b. Everything else uses 2 pi over b to calculate the period. Okay, any questions on that? All right, so how do we kind of keep all this stuff organized? Well, we want a way to remember the original asymptotes for each function. The tangent, the cotangent, the secant, and the cosecant. So So what I've done here is I've made a chart that gives you all of the asymptotes in the first positive cycle of each graph. And as long as you know what the asymptotes are in the first positive cycle, then you can figure out what happens to them if you do a transformation by setting them equal to the argument. And then if you put plus the period times n, that will describe how often the asymptotes repeat. When you're describing tangent and cotangent, since there is only one asymptote per cycle, your answer would only have x equals, and that would be it. If I ask you to describe the asymptotes of secant and cosecant, we generally want to set up two equations. The reason we need two, one asymptote, or one equation, will describe what's happening to, say, the left asymptote, and the other equation will describe what's happening to the middle asymptote. Technically, there is a way to describe what's happening to both of them with just one equation. That gets a little, you'd have to think about it a little bit to figure that out. But if you do it this way, it's okay. So we have two different asymptotes in secant and cosecant, and we're going to describe them with two separate equations. Not the most optimal way to do it, but it's a little easier than trying to describe it with one. Any questions on that chart? All right. So let's take a look. I think I got a couple more examples. So it says find the domain, the range, the period, and the vertical asymptotes of secant. No transformation. Okay, just basic secant. Domain, range, period, and asymptotes. All right, let's start with the period. What's the formula we use to find the period of secant? John?
2 pi over b.
2 pi over b. And what's b in this case?
1.
1. Okay, easy enough. So the period of the natural secant function is 2 pi. All right, let's now describe the range. Let's go back and look at it. Does secant go up forever?
Yeah.
Okay. Does it go down forever?
Yeah.
Yep. Okay. Does it hit everything in between?
No.
No. There's a gap. There's a gap right between those two red lines. It never hits anything in that section. How could I figure out, it doesn't matter which one we look at, but let's look at this one. How could I figure out how high it's going right there? What could I do? Yep.
You calculate a local maximum.
I could calculate a local maximum. And how could I figure out how low it's going right there? Yep.
Calculate local minimum.
I could calculate a local minimum. Now, if I zoom in a little more, can anybody tell by looking at the graph, probably easiest to look at the one in the middle for the local minimum, how high do you think that y value is? Where is it? Yep.
Negative infinity to -1.
Yep, it is going up to -1. So we have anything from negative infinity to -1. That's the bottom part. And it does hit -1. So we can include it. And what about the top part? How would you describe that? Caleb?
1 to infinity.
It is. If you find the local minimum there, it is 1, and it goes from 1 to infinity. So the range is basically every number except numbers between -1 and 1. It never hits inside there. Okay, so there's the range. asymptotes. Well, we don't really have to do anything too fancy because we're not doing a transformation. So let's just go back and look at the table. Secant has asymptotes at pi over 2 and 3 pi over 2. So we're going to start with those two. And how often does each asymptote reoccur? In general, every what? Yep.
Pi over 2. I mean 2 pi.
Yeah, every cycle. Well, what's a cycle in this case? Every 2 pi. So this asymptote is going to repeat every 2 pi units, and this asymptote is going to repeat every 2 pi units. Now, let me show you something quick that you could do. So the first one is pi over 2. If you add 2 pi to that, so let's do it right here. What's the common denominator? 2. Multiply by 2, multiply by 2. What's pi over 2 plus 4 pi over 2?
5 pi over 2.
5 pi over 2. So looking at the top one, the first one you get is pi over 2. The second one you get is 5 pi over 2. Any guess what the next one would be? What is it?
9 pi over 2.
It would be 9 pi over 2. And how about the next one after that? 13 pi over 2. So that's the pattern of asymptotes you get in the top one. And you could also subtract and go the other way. Now look at the bottom one. This is 3 pi over 2 plus multiples of pi. So the first one we had was 3 pi over 2. What's 3 pi over 2 plus 4 pi over 2? 7 pi over 2. So you're going to get an asymptote there. What would the next one be? 11 pi over 2. And the next one? 15 pi over 2. It's perfectly fine to describe the asymptotes with two different formulas, but you really don't need to. Because if you look at them together, you have an asymptote at 1 pi over 2, 3 pi over 2, 5, 7, 9, 11, 13, 15. It's all odd multiples of pi over 2. That's a simpler way to say it. Okay? It's okay to say it with two separate equations, though. But I'm just trying to show you, you could do it with just one equation. And the equation would look, what would it be? Pi over 2 plus, let's see, what would I add to get 3 pi over 2? Pi. If you wrote your asymptotes like this, that single equation combines those two into one. Because now, the first one you would get here is 3 pi over 2. Then the next one would be another 2 pi over 2, so that'd be 5 pi over 2. Then if you add another 2 pi over 2, you get 7 pi over 2. So this works perfect and is a little more elegant than two separate equations. Okay? But I'm okay with that, the two separate. All right, so we have the range, the period, the asymptotes. What's the domain here? Is it all real numbers? Like sine and cosine? No. What are you not allowed to include here? Yeah?
The 2 pi plus pi.
The two. Can you say that again?
The equation we came up with, the pi over 2.
Oh, yes, this one. Yeah, you can't include the asymptotes. So basically, that's how I would describe the domain. I would just say it's all real numbers except the asymptotes. And I would write it just like that. All reals except the asymptotes. If you want it to be a little bit more formal, you could say all real numbers except numbers of the form, and then write these two equations down. All real numbers except numbers that fit this pattern, because if it fits this pattern, it's an asymptote. Any questions on that? All right, let's see. Cosecant is pretty similar. So the only thing that would change here, if we did cosecant, the domain would be the same. All real numbers except the asymptotes. The range would be exactly the same. The period would be exactly the same. The only thing that would be different is those two numbers. Instead of saying pi over 2 and 3 pi over 2, because we did secant, you would put in the 2 for cosecant, 0 and pi. But that's the only thing that would change. Any question on that? Okay, so we'll skip that. Okay, so this one tries to show a graph and find the period and the asymptotes. Okay, start with the period. What's the period of y equals cosecant 3x? John?
Would it be 2 pi over 3?
2 pi over 3. And the asymptotes? Can somebody tell me for cosecant, what are my two original asymptotes? Okay?
0 and pi.
0 and pi. What do we set each asymptote equal to and then solve to figure out where it's going to move under that transformation? Yep.
The 3x.
Yeah, set it equal to the argument. Well, if you have an asymptote at 0 and you horizontally compress that by a factor of 3, nothing happens. It was at 0, it stays at 0. So one of my new asymptotes is going to be 0. The other asymptote, okay, originally it was pi. We're going to set it equal to 3x. And how do we solve for where that one's going to move? Yeah.
Divide both sides by 3 and you get pi over 3.
Yeah. It was at pi. You've compressed it by a factor of 3. Now it's at pi over 3. So there's your other asymptote. Now, in general, those two asymptotes are going to repeat how often?
2 pi over 3.
Even more general. They repeat every... Yeah?
Period.
Every period. They're going to repeat every single period. So it helps that we already know the period, which is what enable you to set every 2 pi over 3. Technically, you don't need to do 0 plus because that doesn't change anything. But those two asymptotes will repeat under that pattern. Now, if I wanted to show 2 cycles, is that what they wanted? 2 periods? What would my width of my window have to be to show 2 periods? Yeah.
4 pi over 3.
4 pi over 3. So let's set this to 0, and we'll set this to 4 pi over 3. And as far as up and down, not really important because it's going to go up and down forever. -4 to 4 is pretty good. But we should see exactly 2 U-shapes. I must have not typed in the function. Nope. You always have to type it in. Cosecant of 3x. 1 divided by sine 3x. All right, so we should see 2 U-shapes and 2 N-shapes. And that's exactly 2 cycles. Any question on that? All right, let's see. So, all right, solving on the calculator. All right, so this kind of reviews a little bit of what we did towards the end yesterday. How do we solve on the graphing calculator? Well, yesterday we focused on a certain window. Okay, we said, okay, just list all the answers between 0 and 2 pi. But really, if you were to zoom out, and you say you had a horizontal line and a wave, how many times would they cross each other if you zoomed out forever? Yeah?
Infinite.
Infinitely many. And So basically, if it crosses one time, it's going to cross infinitely many times because the picture is going to repeat itself forever. If you had, let's say, something like this. Here's a horizontal line. Actually, let's make it even simpler. Let's just do it like this. Hits it right at the top. When is the next time that answer is going to occur? In general. Because I don't have any numbers on this. Yep?
2 pi.
We need kind of more general. Yep?
Next period.
The next period. Whatever that is. Could be 2 pi, it could be pi. We don't know how this graph was made. But the point is, that answer is going to occur again exactly 1 cycle later. And then it'll occur again another 1 cycle later. So when you're solving a trig equation, if they want you to write down all solutions, not just 1, not just 2 in a certain window, this is how you do it. It's very similar to how we wrote down asymptotes. I think I accidentally deleted the page. Hold on. Hold on. So, if they ask you to find all solutions to an equation, not just one specific one, you do it just like you do the asymptotes. Find one solution using second calc intersect, just like we did yesterday, and then put plus the period times n. That tells me you know one of the solutions, and you're telling me that that solution is going to repeat every cycle. And n can be a negative number, which would mean it would be occurring in cycles before as well. Right, let's try one like that, and then that'll be it. Find all solutions. All. Not just 1, not just 2. I want all of them. So you're going to be looking for an answer that has plus period times n on the end of it. All right, so let's do cosecant equals negative 1.6. Well, type in cosecant, I have to do 1 over sine. And let's do negative 1.6. Now, I find setting the window helps me because then I don't look at answers I don't need. What's the period of cosecant? Yep.
2 pi.
2 pi. So let's not look outside of 1 cycle. We only need to find the answers in 1 cycle and then put plus the period times n. So let's focus on just the first cycle. There's a U shape, there's an N shape, and I want to figure out everywhere that it hits negative 1.6. How many times does it hit negative 1.6? Yep. It will hit infinite, but how about just in that one window? 2. So I need to write down 2 general solutions. Let's find the first one. Here is the first one. 3.82. That's the first one. And now, what did we just say the period of cosecant was? 2 pi. So that answer is going to repeat forever, every 2 pi units. So if you wanted to know the next time it occurs, add 2 pi to that. If you want to know the next time after that, add 2 pi again. All right, so now we've described this answer forever. Now we need to describe this one. Not just describe it, but describe it forever. Okay? So we're going to do second calc intersect. and we get 5.61. If that's all you wrote, is 5.61, you haven't answered this question. You've answered where it occurs in the first cycle. So then tell me that that answer repeats forever. And those are your two answers. It's basically exactly like writing an asymptote, except you have to use intersect to figure out the number. Okay, that's it. Any questions on that? Okay, so here's the homework from section 6.4. If you already did some of those questions in last night's homework, you don't need to do them again. But whichever ones you have not done yet, just add those into the homework you've already done. And we'll take a look at that tomorrow. Okay, so don't forget too that there's a test tomorrow on section 6.3, 6.4, which is all graphing, sine, cosine, tangent, cotangent, secant, and cosecant.